All right, the next set of reactions with alkenes, we're going to talk about oxidations and reductions. We're talking about a couple of different types of oxidations and then one final reduction. So what happens in an oxidation? You're simply adding bonds to oxygen. In a reduction, you're adding bonds to hydrogen. So what does this look like practically? So they say you start with an alkane, so practically this, with 3 bonds to hydrogen. If it was going in this direction, going back in the blue is reduction. If it was going to oxidize it, we would add a bond to oxygen. So we turn from an alkane to an alcohol. And we want to further oxidize this. Again, remove another hydrogen. We would get a aldehyde. And then one more oxidation, getting rid of that last bond, CH bond, we would get a carboxylic acid. All right, so oxidation, and then moving backwards, adding bonds to hydrogen. These are reductions, these are reductions. All right, so if we start with something that has 3 CH bonds, we can replace that with 3 bonds to oxygen to get all the way to a carboxylic acid. What if we only have 2 bonds, 2 CH bonds? Well, we can only oxidize it twice then. Right, we can only switch, right? Adding bonds to oxygen is oxidation, adding bonds to hydrogen is reduction. So in this case, we only have 2 bonds there to hydrogen, so we can replace those one at a time. The first one would be, again, replacing one of those, turning it into an alcohol. And if we did another oxidation, we would turn that alcohol into a ketone. Reduction is going back the other way. But because there's no more CH bonds left, we can't continue oxidizing. Here we start out with 3 CH bonds, so we can replace those 3 CH bonds with 3 different CO bonds. Here, 2 CH bonds, 2 CO bonds, a pi and a sigma. So oxidations will be learning how to take some of these and do oxidations. Reductions will be learning how to take some pi bonds and turning those into alkanes. So the first reaction we're going to learn is actually an oxidation. So this is an oxidation. It's called an epoxidation because it forms an epoxide, which is a 3-membered ring with oxygen. That's an epoxide. So it just creates an epoxide. So it's oxidizing the pi bond, adding bonds to oxygen, doing an oxidation, and it uses a perbenzoic acid. The second oxygen, this OO bond, the second oxygen is an electrophile. So let's take a look at that. So a lot of times you'll see MCPBA. So let's look at the mechanism now. So the mechanism involves the formation of an epoxide, and it involves essentially the pi bond being the nucleophile. We talked about the first one of the oxygens as the electrophile, so the pi bond reacts, attacks that oxygen. At the same time, the OO bond breaks, forms a new pi bond between carbon and oxygen. The original pi bond between the carbon and oxygen goes for the H, and those electrons between the O and the H go for the other carbon. So we have 1, 2, 3, 4 arrows being moved, and 4 different bonds being formed. So keep track of these. You see, there's the blue oxygen that ends up right here. The green electrons form that bond. The purple electrons are now a pi bond. The blue electrons are now forming an OH bond, sigma bond. And the gold electrons are between the oxygen and the carbon right here. This all happens at once. It's a concerted process. With 4 arrows. Make sure you know 4 arrows, critically important. Take some time to practice on another piece of paper to watch these 2 green electrons go to the oxygen, form that sigma bond. The purple electrons break the OO bond, that forms a new pi bond between C and O, right there. The pi bond electrons are blue. They go and grab and form a new OH sigma bond. The gold electrons between the oxygen and the hydrogen now come back and form a bond between the oxygen and the carbon, and they're shown there. Practice this on a piece of paper. And it's always a concerted mechanism, and it's also a syn addition. You'll notice that. It's a syn addition. Syn addition as well. Again, just to emphasize this syn addition, if you start with a cis alkene, when the epoxide is formed, if the H's are on the same side before, they'll stay on the same side. If the H's are on opposite sides, they'll be on opposite side of the epoxide. The epoxide can either come from the top or the bottom, so they also would have had this enantiomer as well in both cases. So it's very similar to the BR2, the halogenation reaction as well. So again, I just want to show this epoxidation mechanism again. So the first step, the pi bonds by nucleophile, it reacts with the oxygen. The OO bond breaks and forms a new pi bond between that carbon and oxygen. The pi bond here goes and grabs the hydrogen, and the 2 electrons between the O and the H come back around and get to the other carbon. 4 arrows concerted. We get a syn addition. This is stereochemistry. It's a syn addition. 4 arrows. It's called an epoxidation, and we end up making an epoxide. And if we had, right, we started with this alkene, the H's were trans to each other, and so they would be trans in the final product as well. And you'd also get this here. Pen to paper, practice drawing these arrows. It's an epoxidation mechanism. Concerted, syn addition, right? You're adding an oxygen. And the final product here, another thing to make sure you're doing this right, what will the final product be? The other final product? You will have a carboxylic acid. So you can see this piece that's left over turns into a carboxylic acid that's down here. That's the other thing that's formed. Make sure you form that as well. Well, the epoxidation formed a 3-member ring with oxygen. Now let's look at ways to do an oxidation where we get an alcohol, right? We turn something into an alcohol. In this case, a diol, vicinal diols. Again, we're going to have, this is called oxidation with osmium. So osmium oxidation gives diols. It's a syn addition. The syn addition, osmium, gives diols. You're responsible for only knowing the first step of the mechanism, which is shown here. So 3 arrows. So you're responsible for knowing these 3 arrows. So 3 arrows. And what happens here, the pi bond reacts with the oxygen of osmium. The pi bond between the oxygen and the osmium breaks, putting a lone pair on this osmium. At the same time, this osmium oxygen pi bond moves there, and we form this 5-member ring, this cyclic osmate ester. I want you to know this. You do not need to know how to do this, so you're not required to know this mechanism here. You need to know that you get a syn diol, and the oxygens are right next to each other. The carbons right next to each other. So in this case, you're adding 2 OHs in a syn fashion, 3 arrows. You get we call this a diol. So this is the osmium oxidation, responsible for knowing this part of the mechanism. The third oxidation that I want you to know about is oxidation with KMNO4, shown here. O4 is the key because we're going to add 1, 2, 3, 4 oxygens. So you see KMNO4 in a pi bond. What I want you to think about is breaking that in half, right? And you turn those into carboxylic acids if there's H's here. They'll be oxidized all the way to carboxylic acids if there's H's present. In a different sense, so you cut that in half. So we numbered our carbons. 1, 2, 3, 4, 5, 6. It will be 1, 2, 3, 4, 5, 6. You know it's carbon 1 and carbon 2. Carbon 1 and carbon 2 had an H to begin with, and now they do not. We replace that H with an oxygen. We fully oxidized it. If it had been a different structure with KMNO4, This would not give carboxylic acid because now there's no H's here. These are methyls. We would cut this in half, and we would get, maybe just to draw it a little simpler looking, we would get 2 ketones. I'm going to bring our carbons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So depending on what we have, KMNO4, if the alkene has hydrogens on it, you end up with carboxylic acids. If it doesn't, you end up with ketones. So that's why it's always important to draw in hydrogen on the alkenes. It'll tell you a lot. It makes you keep track of things as well. So in this case with KMNO4, so this is the reagent to remember. You cut an alkene in half. You turn it for sure into a carbonyl, C double bond O. And if it has H's, you put an OH there. If it doesn't have H's, you make ketones. Another method to make ketones instead of carboxylic acids, say you wanted to not make carboxylic acids, but you had an alkene that had a CH, right? So there's a H here, and if we use KMNO4, that would turn that into a carboxylic acid. Well, if we want to keep it as an aldehyde, in that case, we would use O3. Ozonolysis in this reductive workup. You're not going to be required to know this one. I'm not going to ask you to know that. So we're going to differentiate these, so don't worry about this. So KMNO4 kind of covers that for us already, so we're not going to need 2 reagents. O3, what O3 is going to do, is going to again take an alkene, split it in half, and instead of oxidizing all the way, it's just going to turn it into 2 carbonyls. And it does this with ozone, O3. Right? Please be sure to know how to do these resonance structures. Know these resonance forms and be able to draw them. Be able to draw those resonance forms. All right, let's take a look at the ozonolysis mechanism, the first step that you're going to be required to know. For the first step, again, you have a pi bond, that's your nucleophile. It's going to react with O3 in this resonance form shown here. So even though there's a plus charge in this oxygen, it's actually electrophilic at this oxygen. Right, so how would this work? So these electrons are going to go from the pi bond to that oxygen. It's going to break the pi bond between the 2 oxygens, and that's going to give electrons there, which is great, right? Because it was missing electrons, that's why it had a plus charge. And this oxygen in the end is going to react and go there. So it's going to be a syn addition, 3 arrows. It's concerted, it happens all at once. There's no carbocations. And what is the product going to look like? Well, we're going to have, instead of syn addition, it's going to form a 5-membered ring. Like this. This 5-membered ring, so this is called a 1,3 dipolar addition, which you don't really need to know. But from this point, I don't need you to do anything else. I just want you to be able to do, and draw on our H's, this first step. Be able to do this first step, very similar to that osmium one. Just want to be able to see that first step. The osmium also had 3 arrows, so it was concerted. Just want to make sure you can see how this works. Ozonolysis can be really easy to see working forward and backwards. And if you just look at a pi bond, what they'll tell you to do, if you see O3, right, they'll just tell you to think about it being clipped. Right, you can see kind of those both turn into carbonyls. And then you separate them out. And you can just see those from here on out. The other thing to do, if you see these two, to work backwards, you'd say, oh, if this was carbon 1 and this was carbon 2, what this could have came from would be getting rid of these two and just making a bond between carbon 1 and 2, and that would tell you what alkene it came from as well. So that's another thing to think about. Don't need to worry about this button down here. That's that's a different step. So really just focus on this. Find that pi bond, cut it in half, make them carbonyls, and then you can also work backwards to see what alkene it came from. You only need to know the mechanism for the first step here. Mechanism for the first step, adding the O3 to the pi bond that I just showed you. All right, last and final reaction for the chapter. This is that hydrogenation. This is a reduction. So this is hydrogenation. This is actually adding hydrogens, hydrogenation. So we're going to do a reduction or we're going to add CH bonds. So we're going to take a pi bond. You don't need to know the mechanism for this. All you need to know is that when you add palladium on carbon and hydrogen gas, you're going to get a syn addition. And you're adding, in one step, 2 hydrogens. So this is concerted, no carbocations. And you're just going to turn an alkene into an alkane, and the H's are both going to add syn. That's all you need to know about how this works. Their mechanism, I don't really know if this is true or not. If you take advanced organic, I'll tell you more about it.